That's cool.
I know, I noticed.
I just noticed that.
I like, that's the first thing I always look for.
Let's get started. It's a pleasure for me to introduce Abigail Vieregg from the University of Chicago, who's the speaker today. Abby is professor of physics, astronomy and astrophysics. You have a long title at the University of Chicago, and she is also the David Schramm director of the Cavell Institute there. Abby had got the AB from Dartmouth, and then a PhD from UCLA, and then was NSF postdoc at at Harvard. I should add that actually we even tried to hire her many years ago. And we didn't succeed, and I'm thinking that the reason must be that she does all her experiments on ice and at the polar regions, and so being in Chicago has gives less of a thermal shock every time you travel, and that's why we lost that one. Yeah. She's received many awards, but also and she's PI on several both ground and balloon-based radio, ultra-energy, neutrino experiments or detectors, which I imagine is what she's going to tell us about today. Thank you.
Well, thank you for having me. It's really just a pleasure to be back. I was here a couple of years ago, but it was sort of just on the tail end of the pandemic, and it was much quieter around here the last time I was here. So it's really nice to see everybody and be back to tell you about what we're doing in my group and in the collaborations that I work in, and sort of in this field broadly speaking. So as Giorgio alluded to, I'm going to talk today about how you might try to discover the highest energy astrophysical neutrinos. I'm an experimentalist. That means I try to think about the science that we're doing, analyzing the data that we're collecting, and building the instruments so that we can advance the field. So I just want to start the story here by talking about the science that we're doing and why it's interesting, or at least why I find it interesting. And I wanted to start here. I think, when you talk about neutrino astronomy, you kind of, or at least I think about what has neutrino astronomy done so far for us. And these are some of the things that neutrino astronomy has done so far for us. In particular, I think it's really important to remember that observations of solar neutrinos, that's what we're looking at on the left, is the sun and the light of neutrinos as measured by Super K, which is a big neutrino detector in Japan. The observations of solar neutrinos ultimately led us towards the idea of neutrino oscillations. So Ray Davis built his Nobel Prize winning experiment in a mine where he put a big vat of stuff and waited for neutrinos, electron neutrinos from the sun to interact and look for their signals. But what he saw was a deficit of neutrinos, about 1/3 the number that you expect from astrophysics, he saw. And we know now that that's because those neutrinos were oscillating into other flavors that his detector wasn't sensitive to. So if you build an electron neutrino detector and look for neutrinos from the sun, you see this deficit, and ultimately that led us to learn something about particle physics. So from neutrino astronomy, just by looking at the sun, you learn a sort of fundamental law of particle physics that for neutrinos, the mass eigenstates are not equal to the weak eigenstates, and neutrinos have mass. So that's sort of an incredible thing. And then, later in 1987, supernova 1987A went off. And this is just a picture of the supernova remnant from Hubble. And just from measuring neutrinos from this one event, which went off relatively nearby in the universe, by measuring the spread in arrival time of the neutrinos that came to detectors here on Earth, you can learn about what the neutrino mass is, actually. So you can place neutrino mass limits from just that one event. So again, you learn about particle physics itself from measuring neutrinos coming from outside the Earth and its atmosphere. So that's sort of the early history of neutrino astronomy. And then in the last 15 or so years, neutrino astronomy has been dominated by this experiment called IceCube. So I actually don't work on IceCube, but I think that it's important to lay the groundwork of where we are as a field before I tell you about what we're spending our time working on now. So IceCube is a big neutrino detector at the South Pole. It's actually, I think it's an amazing feat of engineering. What they've done is they've drilled holes down 2 kilometers into the ice at the South Pole, and they lowered photomultiplier tubes down into these holes. That's what these are. That's what these are at the, this isn't connected, that's okay. That's what those are at the bottom, is strings of photomultiplier tubes put down holes. And what they do is they wait and look for neutrino interactions in the ice that make particle showers, and then you look for the Cherenkov emission from those particle showers lighting up your photomultiplier tubes. So what IceCube has done is discovered astrophysical neutrinos. So this is a relatively old plot, but I actually like it because it's pretty straightforward and it shows the point, which is that IceCube has observed as a function of energy a flux of neutrinos. That flux of neutrinos is from atmospheric neutrinos and then the astrophysical neutrinos on top of that. So they're seeing a significant excess above atmospheric neutrinos. And that's the discovery of astrophysical neutrinos. So just to put this in a nutshell, in 2013, the first astrophysical neutrino events were observed about 10 years ago. And now they've measured a spectrum with energies up to about a PeV. So you're going to have to get used to thinking about big energies for this talk. So a PeV is 10 to the 15 EV, and we're just going to go higher from there. So I'll tell you all the prefixes as we go higher from there. But a PeV is 10 to the 15 EV. That's sort of the highest energy neutrino that IceCube has seen thus far. IceCube has also seen steady sources with neutrinos. So IceCube has seen a couple of years ago, they put out this really nice result that was the first detection of a steady source in the light of neutrinos. This is an active galactic nucleus called NGC 1068, measured with 4.2 sigma significance by IceCube. And there are neutrino excesses at other locations at lower significances. So it seems like as IceCube is collecting data, sources of neutrinos on the sky are starting to pop out. So you might ask the question, why NGC 1068? What's special about this thing that, here's a picture of what that looks like with Hubble. What's so special about this active galactic nucleus? I think, it's one thing you might guess would be that the first source to pop out in the light of neutrinos, high energy neutrinos, might be a source that's very bright in gamma rays. But it turns out that NGC 1068 is not really special in gamma rays. It's not the brightest thing in the sky in gamma rays, but it is quite bright in neutrinos. So it sort of leaves us with some questions, right? Why is that the case? And we'd like to figure out sort of what are the sources that are giving us astrophysical neutrinos, and what is the nature and cosmic distribution of these sources? So like, what is the physics that's driving the central engines of these sources that's producing these very high energy particles? And then I think if you flip the question around, that's sort of the astrophysics case, but if you flip the question around and ask what's the particle physics you can do, there's fundamental, you can learn things about fundamental particle physics itself by looking at neutrinos or particles at an energy range that no one has seen before. So I'll talk a little bit about both of those. So I'm interested in particular in measuring the high energy universe. Yes?
So when you're talking about astrophysical neutrinos, do you just mean the high energy ones? Because you said like the first observations were in 2013, but we'd seen them from the sun significantly earlier.
So I'm talking about high energy astrophysical neutrinos from not the sun, but from energetic sources, I suppose. Yeah, probably outside our own galaxy. Yeah. Okay, so let me also try to maybe answer that question on this slide also, which is that, I think in particular I'm interested in thinking about the highest energy sources of these particles. And we know that there are sources in the universe, outside our own galaxy likely, that are making ultra high energy cosmic rays. So there are charged particles that we see out to about 10 to the 19, a little over 10 to the 19 EV in charged particles, likely protons. And that's shown here with the green on the right. So that's the ultra high energy cosmic ray spectrum that we've observed. The IceCube neutrino spectrum is the pink in the middle, and then the gamma ray flux that we observe is the blue on the left. And it's interesting to think actually that we've seen really high energy cosmic rays. We've seen neutrinos not out to that energy yet, but there's no reason to believe, in fact there is reason to believe that they should be out there. We just haven't quite yet built the instrument that can measure them. And then we've seen gamma rays, but not out to those energies. The reason we haven't seen gamma rays out to those energies is that gamma rays that come from far away in the universe at those energies would be obscured. They wouldn't make it here. They'd scatter off the light in between us and those places, and so they wouldn't make it here. But the question we'd like to try to answer is, for these high energy sources that are making these high energy cosmic rays, how are particles accelerated, right? Is it active galactic nuclei, which are black holes accreting mass at the center of galaxies? Is it blazars, which are jets of particles emitted in our direction by AGN? Is it gamma ray bursts, which are the most luminous events in our universe? Or is it something else not on this list? And I think if you asked, 5 different theorists, they might give you 5 answers as to maybe more than 5 answers, as to what the possible sources of the highest energy particles are. Okay, so neutrinos are, I would say, a new window onto the ultra-high energy universe. So we've measured ultra-high energy cosmic rays, but the problem with cosmic rays is that they're charged particles. So if you have, there's 2 problems with cosmic rays. One problem is that they're charged particles. So if you have a cosmic ray coming from an extragalactic source far away, and it comes through our Milky Way to us, the direction that it came from gets scrambled by the magnetic field in the Milky Way. And so when you go here on Earth to point back where those cosmic rays came from, it's hard to figure out where they came from. So that's one nice thing about neutrinos, is that they're unaffected by magnetic fields, and so they point back to where they came from. The other thing that's really nice about neutrinos is that they propagate really, really far through the universe. Because they're weakly interacting, right, that same thing that makes them really hard to detect actually in the end, which we'll get to in a minute, how you build a neutrino detector, the same thing that makes them hard to detect makes them a really beautiful messenger particle for the distant universe, because they can come all the way to us without hitting anything else and carry the information about where they came from. Okay, so in the highest energy range, ultra high energy neutrino telescopes would open a unique view into the universe, complementary in the multi-messenger astrophysics landscape of cosmic rays tell you one thing, neutrinos might tell you different information. And what ultra-high energy neutrino astronomy would do is give you the highest energy observation of extragalactic sources. It would allow you to look at sources far away that you can't look at any other way, because protons get scrambled in magnetic fields and photons scatter before they get here and lose energy at those high energies. You can look at very distant sources, and I actually like this third one. You can look deep into opaque sources, which means if you have a really dense source that's making high energy stuff, the neutrinos that are made in the middle will come right out to you, and you can see them. But other particles that are made in the middle will scatter in, let's say, the dust surrounding those sources, and you might not see those. So it's like a window into what's happening in the central engines of sources. Okay, so I think it's also fun to think about some of the particle physics that you can do with neutrino astronomy. And I kind of like this cartoon on the right, because one example of things you can do is actually try to measure the neutrino cross-section itself at extremely high energies. So we're looking for particles that are like 10 to the 18 eV, much higher energy than you can make at the LHC here on Earth, even in the center of mass frame. So like even once you take this fixed target experiment where you have this 10 to the 18 eV particle hitting a nucleus, even once you go to the center of mass frame to compare to the LHC, it's still much higher energy than what you can get there. And so that allows us to probe neutrino physics, right? Like the neutrino nucleon cross-section in an energy regime you can't make an experiment here on Earth to do, or at least we have not yet made an experiment here on Earth to do. But you might be thinking that this is a little nuts, that trying to measure neutrino cross-section sounds a little nuts, which, okay, measuring the absolute rate would be really hard. So what you do is something that I always tell my students, is you make a relative measurement whenever you can. You never try to make an absolute measurement if you can make a relative measurement. And so the relative measurement we make is actually counting the number of neutrinos that come through the Earth this way compared to the number of neutrinos that would come the other way. So we use the Earth itself as like a cross-section analyzer. So you can just calculate what the cross-section is in the Earth by making this relative measurement. So that's kind of one fun thing to think about. Another fun thing to think about is if you had flavor tagging, if you could tell what flavor of neutrino you were measuring. which it turns out, might be possible by measuring basically the emission that you see and how the shower profile develops from the neutrino interaction, is you could probe neutrino oscillations over extremely long baselines, right, like cosmological baselines, and you could look for things like neutrino decay, just certain flavors of neutrinos decay over cosmological distances. So this is just one plot of the neutrino cross-sections as the neutrino cross-section as measured. So over an enormously wide energy range, right, the neutrino nucleon cross-section has been quite well measured at low energies. At a little higher energies, the error bars get a little bit bigger, and that's an experiment called PHASER actually at CERN. And then at even higher energies, there's actually measurements from IceCube, which I told you has measured astrophysical neutrinos. They've done this measurement, right? And then out at even higher energies, if you could make a measurement of the cross-section here, you could constrain the models, in an energy range. It's like you have a larger lever arm because you're coming from really high energies to constrain the parameters in these models. Okay, so how are neutrinos made? So one way that ultra-high energy neutrinos made are through something called the GZK process. So the GZK process, this is like a classic exam question on your special relativity undergraduate final exam, where you ask, if you have a proton moving with a lot of, has some energy, and it hits a CMB photon that's a known temperature, and it has to then make a particle called a delta that has a certain mass, what's the energy threshold for that process, where you take a proton, slam it into a photon, make a delta resonance? It turns out that the energy threshold for that is about 10 to the 19.5 eV. And so what that means is that cosmic rays above about 10 to the 19.5 eV interact with a CMB photon, make a delta resonance, and then the delta decay chain ultimately gives you neutrinos. So the other way to look at this in like the cartoon version is that you have cosmic rays and you have the CMB, and that gives you a neutrino beam. And I actually like to think about this in even a different way, which is that this is not too dissimilar to the way they make neutrinos at Fermilab, right? You accelerate some protons, slam it into a target, and you get neutrinos out the other side. And so we're basically making an ultra-high energy neutrino beam from every source of cosmic rays in the universe, just because the fact that the CMB exists. So one question you can ask by looking at the neutrinos that come from this process is, what's the high energy cutoff of our universe? What are the highest energy cosmic rays that are being made? Because remember, the cosmic rays that get turned into neutrinos through this, we don't see those cosmic rays anymore. What we see is the byproduct from neutrinos. So you can't ask the question by looking at cosmic rays. You can only ask the question by looking at the byproduct in neutrinos. Okay, so where do we stand today? This is a plot that we made yesterday because IceCube just put out new results like 3 days ago with the current best constraints at the highest energies on the neutrino flux. So the best constraints as of this week, it was true before, but now it's even more true. The best constraints come from IceCube up to about 10 to the 19.8 eV. So all the way at the right-hand side of this plot, I'll talk about that experiment called ANITA in a little bit. But over a very wide energy range, IceCube rules the day, still. IceCube is the best experiment that is producing results all the way out to the highest energies. They've obviously made measurements at the lowest energies here, and they've made an upper limit out to the highest energies. And there are various models on this plot of where you might expect neutrino fluxes to come from. It's kind of a funny plot because normally what you do is you take all the models that are ruled out and you don't put it on the plot anymore. But because we just updated the limit yesterday, there's still models. Now those models have been ruled out, those ones at the top, right? So we'll figure out what those are and adjust it. But you see there's actually quite a bit of phase space to go to probe the parameter space where we expect to see ultra-high energy neutrinos. So that's where we are. The other thing that's kind of interesting that's happened in the last year is there's another experiment that's in the Mediterranean Ocean called KM3net. That's similar in concept to IceCube, but it's a bit smaller, and it's in water instead of ice. So about a year ago, KM3net, maybe it was only 6 months ago, KM3net put out this set of slides that shows that they've seen a massive event in their detector. So one event, sometime in the summer of 2024, they saw this massive event of what looked like a nearly horizontal muon going through their detector that would be consistent with a muon from an astrophysical neutrino interaction. Someone else has gone through and tried to put where that event sits on that limit plot. So if you actually look, there's the IceCube limit that just came out last week. And then if you look, the KM3net event is actually above it, which is weird, right? IceCube ruled out that phase space, and then KM3net is coming in and saying we saw an event there. So this is an interesting thing, and I think one thing that to note is that actually tomorrow KM3net is having a press release where I think they'll put out the paper finally from this event if you're interested. So maybe we'll learn more tomorrow about what the nature is of this event and whether they think it's consistent with the IceCube result or not. Yeah.
How do you get a flux from one event?
You have a really big error bar. So so how do you get a flux from one event? You have some Monte Carlo of your detector, right, that tells you, what the expectation is, and then that's like what, a whole order of magnitude error bar, right? So this is some third party that went through, took the one event and tried to do an analysis of it. We'll find out tomorrow what the paper says. Yeah. You end up with a really big error bar, I think is the short answer. I bet their paper will also show something also with a big error bar, is my guess. But, okay, so that's where we are. We have this nice limit from IceCube, this one sort of tantalizing event from KM3net all the way out to higher energies than IceCube has ever seen. But the question for me is really, what do you do next? And, I would argue that there's a problem with neutrino astronomy. And that's that neutrinos don't interact very often. They're weakly interacting. They're really hard to detect. And so you need a huge detector to see anything. And so that's what the community has done, is we've built IceCube and KM3net, these really big, Cherenkov detectors. And so if you want to go to even higher energies, the problem is that the particles are even more rare, right? Like everything in astronomy is a falling spectrum. And so if you want to go to higher energies, you're stuck because the particles are even more rare. So what that translates to is you have to build an even bigger detector. So one thing you could do, and this is kind of a provocative slide, is build 10 IceCubes. But that sounds, expensive, and also, frankly, I don't have time to wait for that. Like I'm too impatient, and I don't have time to, build something that's that big. So what we've been doing is thinking about other ways to detect ultra-high energy neutrinos. Yes?
Cross-section increases, though.
Yeah, so I cheated a little bit. So the cross-section does increase. So I cheated a little bit. Everything in neutrino is a falling spectrum. The cross-section does increase with energy, but it's still true that you need a bigger detector because the falling spectrum is steeper than the cross-section increase. Yeah. So I did cheat a little bit. Okay. So one way that you might look for ultra-high energy neutrinos, other than making a bigger optical Cherenkov detector, is by looking for, believe it or not, the radio emission that these particles make when they hit a dielectric. So when a neutrino interacts in a dielectric, it makes a particle shower. That particle shower makes Cherenkov emission. But it turns out that if you look at the wavelength of light in that Cherenkov cone, that's bigger than the size of your shower. So the particle shower that neutrinos make is like 10 centimeters wide. That's the size of the Moliere radius of these showers in ice for these energies. And if you look at wavelengths that are much bigger than that, then you get this beautiful coherence effect, where all the little electrons in the shower that are creating radiation, the radiation adds up coherently because the wavelength is much longer than the size of the bunch of electrons. This is called the Askaryan effect. It turns out that the Askaryan effect was measured here at SLAC in 2006. So in 2000, and this is what the emission looks like. So if you put an antenna and if you slam a bunch of electrons into a target and you put a bunch of antennas around it to measure the radio emission, this is what it looks like. This is a plot of electric field versus time. And I like to think about this kind of like you're looking at an oscilloscope trace. Like you have this is really electric field, not voltage, but the way you measure this is by putting an antenna into an oscilloscope, and that's kind of what we're looking at here. So it's a very fast broadband impulse. That's what you get, sort of over a nanosecond time scale. And if you can do Fourier transforms in your heads, then, I'll tell you the answer, don't worry, then you'll know that an impulse like this gives you a very broadband signal. So what we need to do is build a very broadband radio detector that has very fast timing resolution to look for signals like this. So that was measured at SLAC. I thought I would put just a slide up because, you know, when they picked a hotel for me to stay when I came, I asked to stay at the guest house at SLAC. And I always do every time. And it's because I still have a soft spot of like a simpler time when I was a graduate student, spending months at SLAC doing this experiment. And I still love it to this day. And every time I come, I like to stay there. So this is an experiment we did early on in my grad school career where we built a huge ice target that's in the middle. We actually had like an ice sculpting company back its truck into end station A, and then we unloaded it into this like place that we had carved out, and then we slammed the beam into this ice target, and that's what it looks like lit up in the light of Cherenkov emission, right? Cherenkov emission is blue to your naked eye. But it turns out that you can play a trick where, and the money plot from the paper is on the right actually, where you can essentially simulate an ultra high energy shower by taking a bunch of electrons at lower energy. So these were 28 GeV electrons, so that's 10 to the 10 EV. You make a bunch that has 10 to the 9 particles in it, so 10 to the 10 times 10 to the 9 gives you 10 to the 19 EV, so it's like a shower you're depositing. It's almost like you've just taken away the first part of the shower development, and then the rest of it should all be the same in your ice target. So you slam a 10 to the 9 electron bunch into your ice target, watch it develop, and that's what you get. And then it's even better than that. So you can actually change either the number of particles in your bunch or the energy of your bunch. That effectively changes your shower energy. That's what's on the x-axis. And then what you see on the y-axis is that the amount of power you get in radio, if you count, this goes up, you know, it's 1 order of magnitude on the x-axis, 2 orders of magnitude on the y-axis. That tells you that the power is going like E squared. So that's the coherence effect we were looking for, that the power in radio goes like the energy of the shower squared. And it turns out for extremely high energy showers like these, 10 to the 19 or 10 to the 20 EV, the radio emission dominates over everything else. So it's, even though the Cherenkov emission to your naked eye is blue, for a really high energy shower, the radio wave is a whopping signal because of the coherence effect. All right, so I thought I would just also throw this in. This is for the graduate students. So this is a picture of me still the most ridiculous thing I've done for science. And I've done kind of a lot of ridiculous things for science, which we can talk about later if you want, including like camping on the Antarctic plateau. Still the most ridiculous thing I've done for science is this, which was ironing ice to make that ice target to stick in end station A this was like 3 in the morning because we were like running out of beam time and we needed to get that thing together. So unfortunately I did not electrocute myself. Thank you to Amy who kept me from being electrocuted. The SLAC safety people should close your eyes. Okay, so right, so that's one way that you might look for ultra high energy neutrinos, is by looking for the radio emission that's made when a high energy particle impacts a dielectric like ice. Okay, the other way that you might look for ultra high energy neutrinos is a little bit different. And that's that when an ultra high energy neutrino, when an ultra high energy particle like a cosmic ray or some other particle makes an air shower, a neutrino won't make an air shower, right? It has too low of a cross section. It'll just go right through the atmosphere. But when a particle like a proton or some other particle makes an air shower in the atmosphere, then the particles in that shower get split along the magnetic field lines of the Earth's magnetic field. And that splitting of the particle shower gives you a synchrotron emission. So just from a high energy particle shower in the atmosphere, you get radio emission actually. We see this from ultra high energy cosmic rays in the atmosphere. But the kind of neat trick that someone thought of about 10 years ago is that for tau neutrinos, which is one of the flavors of neutrinos, a tau neutrino can interact in the Earth. About half the time it makes a tau lepton. That tau lepton can escape the Earth, and then that tau lepton can shower in the atmosphere and give you a particle shower that gives you radio emission from synchrotron. And it looks just like an extensive air shower in the atmosphere, except it's coming from the ground. which is really weird, right? A cosmic ray air shower would come from above, but an air shower caused by a tau, that's a daughter particle of a neutrino interaction, would come up from the Earth. So it's like these things penetrate out of the Earth, and if you park your antenna on the top of a mountain or somewhere up high, then you could look for that. So that's sort of the two ways that you might look for neutrinos. Okay, so let's go back to the Askaryan emission, which is this in-ice emission, and we'll just do like a back of the envelope calculation to ask the question, how big of a detector do you need to do this? What do you need to have a chance of measuring the flux of neutrinos we expect? What are we looking at? So if you run through some reasonable, suggestions of what the flux should be, it's sort of 1 neutrino per square kilometer per year, and the interaction length at 10 to the 19 eV, because the cross section is actually quite high, is about 300 kilometers. So it's like 1/100th of a neutrino per cubic kilometer per year. So that means that we're looking at a really big detector if we don't want to wait around 100 years. So we're looking at many, many cubic kilometers of detector. So that means that you need a detector that is radio transparent and dense, so that you can, instrument many, many cubic kilometers of ice. It turns out that ice is great for this because it's not only a dense dielectric, it's also radio transparent, which has that's what's shown on the upper right, is the attenuation length of ice at these frequencies. The reason it needs to be radio transparent is that when you instrument, like imagine putting a bunch of antennas in the ice. If the attenuation length is longer, you can put those antennas farther apart and it's easier to instrument larger volumes. So if we're going for like many, many cubic kilometers of ice, we better have an attenuation length that's sort of at least a kilometer long so that we can have these things spaced out and monitor a large volume. Okay, so that's exactly what we're doing, and people have been working on this for quite a while. I kind of break this down into two different concepts. One is the balloon concept, where you put a bunch of radio antennas on a balloon, you fly it over Antarctica, and you look down at the Antarctic ice to look for neutrino interactions in the ice. The really nice thing about that is that you can monitor a ton of ice. Many, many tons of ice, I suppose. But the balloon flies at 40 kilometers, which means that the horizon is 700 kilometers away, which means that you get to monitor 700 kilometers squared, essentially, of ice all at once, which is a lot of ice. That means that you're going to be able to be sensitive to the highest energy neutrinos. The downside of the balloon is that it's really far away from the interactions. So like the same thing that makes it nice, you can see a large volume, turns out to also be a problem, because the farther away you are, the brighter the signal has to be for you to see it, and that translates to energy. So that means that this balloon-borne concept is going to be the best at the highest energies, almost too high actually. So the ground-based concept is sort of the other way you might think about it, and that's just you put antennas either right at the surface or below the surface, sort of below the snow, to get to clear ice, and you instrument some number of cubic kilometers in an array on the ground. So that's the sort of two things that we're pursuing in this area. Okay, so I promised you a while ago that I would come back to this like best constraints at the highest energies and talk about what's happening in the upper right corner here. So we talked about IceCube, that's the optical detector at the South Pole. But at the highest energies, that way off on the right-hand side of this plot, the best constraints actually come from a balloon-borne experiment called ANITA. And what ANITA did was exactly what I described, which was put a balloon above Antarctica. ANITA had actually 4 successful flights between 2006 and 2016 with a bunch of antennas that are shown on the upper right. Those are quad-ridged horn antennas to make them nice and broadband. We basically flew this thing over Antarctica. We used the fact that we had many antennas to do interferometry to point back where the radio signals came from, so we could ultimately maybe point neutrino events back to the sky. And I just put the results in a nutshell here. Basically, over the 4 flights of ANITA, we did not see an excess above background in the neutrino channel that we went out to look for. We did see a lot of ultra-high energy cosmic rays. That's shown in this plot on the left. That's what a cosmic ray event looks like. That's an air shower event, right? That's a cosmic ray interacting in the air and making that synchrotron emission from the particles splitting in the Earth's magnetic field. And then on ANITA, we saw a couple of weird events that internally we call these mystery events. And what they are is they look like cosmic rays, but they're inverted. You can actually see that right from the plot. So if you look at the blue line on the left and the blue line on the right, they look very similar. They look like cosmic rays in every way, across every analysis cut we can think of, except they're exactly inverted. So you could ask the question, what are those? We don't know what they are, but one hypothesis is that they are, they have some characteristics that are consistent with this tau neutrino coming through the Earth and making the tau lepton and then decaying. There's some reasons they're not consistent with those, but I think one thing to think about is not only would it be nice to build an experiment that would have significant improvement in sensitivity to this Askaryan channel I talked about, but also be able to tell us what those events are, those weird mystery events that we don't know what they are. Okay, so we're doing exactly that. It's an experiment called PUEO, the payload for ultra high energy observations. And for, to the naked eye, it looks the top half looks very similar to ANITA. Okay, except the antennas are smaller, which I'll talk about a little bit. And the magic of how PUEO is a lot better than ANITA is actually all in the electronics, which I'll talk about a little bit. And then we have this big low frequency instrument hanging down below, which is my favorite part of the experiment, because we get to do some fun arts and crafts and build a high bay sized instrument. So I'll talk about that. So PUEO, it turns out that if you play a lot of tricks in the electronics and build a better instrument, you can actually do quite a bit better than ANITA. So the combined ANITA limit is shown. It says ANITA 1 through 4 limit on the upper right. That's the combination from all 4 flights of ANITA. And we think that with one flight of PUEO, we can do at least an order of magnitude better. You can see it right there across the band. And in some places, way more than an order of magnitude. I actually like to think about it, rather than going down on the page, that we're actually pushing left on the page, that we're pushing the energy threshold lower and lower and lower to where there's more neutrinos predicted, basically, which you can see from the underlying predictions. Going left is very interesting on this plot, right? So that's what we're trying to do. I really love this slide because it shows all the beautiful missions that NASA is funding and in the astrophysics fleet, including such celebrities that we all know and love. But then I really love this plot because PUEO made it on there as like this tiny little dot, but there we are. We're in Astrophysics Pioneer's long duration balloon mission, scheduled for launch in December 2025, which means that I probably shouldn't be here giving a colloquium. I should probably be back at my lab in Chicago because we are in crunch time right now, getting ready. It's, February? We're launching in 10 months. Okay, so this is a picture of our team and the institutions involved, just to give you a sense of like how many people it takes to build a mission like this. And here's just kind of a zoom in on the instrument. So it's a 192 channel RF main instrument. That's the quad-ridged antennas, the quad-ridged horn antennas on the top. And we also have this 16 channel low frequency instrument, which is those sinuous antennas, those beautiful patch antennas you see on the bottom. And then we also have like everything else you need to fly a balloon. So you need your instrument, but then you also need, redundant data storage, command and control from the ground, a suite of navigation instruments so you know where you are and where you're pointed, a housekeeping system so you know whether all the voltages are right and whether you're too hot or too cold. And then in-flight calibration from the ground so you know whether your instrument is alive and working. So this is how PUEO works. I talked about this a little bit, where a neutrino interacts in the ice and gives you, a particle shower. It gives you radio emission from the Askaryan effect. So we talked about that. And then we also are sensitive to this tau channel, where a neutrino comes in, makes a tau lepton, and that can come out and make a shower in the atmosphere that we can look for. And then we'll also see quite a few cosmic rays. We'll probably see hundreds of high energy cosmic rays above about 10 to the 19 eV with this thing. Both through the direct channel where we see kind of earth skimming, very horizontal air showers. And then we'll also see radio emission actually reflected off the ice back to us, which is kind of an interesting thing to think about, that actually PUEO is so high that we're above most of the atmosphere. So cosmic rays don't come from above us. They don't shower above us. What they do is shower below us, and then the radio emission reflects and comes back to us. That's actually how we collect most of the area for cosmic rays on this thing. Okay, so we're obviously building on heritage from ANITA, but we've enabled more than an order of magnitude sensitivity increase over, I mean, it's more than that because we're comparing to like the sum of 4 flights, and we're saying that with 1 flight, we can do at least a factor of 10 better across the band. We're doing that by implementing an interferometric phased array trigger. So that is something I'll talk about a little bit. We've also played some tricks to get more antenna collecting area on the payload, and other tricks like real-time digital filtering, and improved pointing resolution because we've made the baselines longer, so we get better pointing resolution. Okay, so I want to talk a little about how you get an order of magnitude improvement over an instrument that, you know, a lot of people, including myself, spent a long time thinking about how to improve. And an order of magnitude comes from a lot of different things. So one thing it came from is getting better antennas. So if you want to build a better instrument, you have to have the best antennas that you can. That's your receiver, right? Like, you can't throw anything away at the antenna if you can help it. So we have 96 quad-ridge torn antennas between 300 to 1200 megahertz, and we can pack more antennas compared to the previous version because they're higher frequency, so they're a little bit smaller. And that's just a trade-off that came from simulations, basically. And here's one of my grad students characterizing and testing all of the antennas in our high bay, getting it ready to go for launch. We also, I would say the big thing that happened in the last few years that made PUEO possible, basically, is by figuring out how to do smarter triggering than what had happened before. So, you know, if you have built experiments, you know that like your detector, in our case that's the antenna, you don't throw anything away at the antenna if you can avoid it. You also try as best you can to have the system have as low noise as possible. So we've worked really hard on our RF front-end electronics to make them better as well. But then the last thing you have to do is throw away as little as you can at the trigger level. You need to have as smart a trigger as you can. And the way we're doing this with PUEO is just going back, it's the oldest trick in the radio astronomy textbook, or maybe it's the oldest trick in the physics textbook, is going to coherence. So if you have multiple antennas, and you know you have a plane wave coming in, then you know the timing that should, like if you have an incoming plane wave, you know what the relative timing should be between those antennas. And so at the trigger level on an FPGA, what we're doing is it's just straight up delay and sum phasing. So we're delaying the signals to a time that corresponds to an incoming plane wave, and then we just sum them. And what that does is it gives us a better signal to noise to trigger on by the square root of the number of antennas. So if you phase 4 antennas, you get twice as good a signal to noise to trigger on, and if you phase, it goes like the square root of n. So this is an old trick. A lot of people use interferometry in different ways. The reason we are using it is to dig deeper into the noise, to get coherent summing of signals so that we can dig deeper into the noise. This actually works quite well. We've demonstrated this on an experiment at the South Pole called ARA, which is a small array of radio detectors at the South Pole. And we built this little instrument that went down there in I can't keep track of years, 2017 or 2018. And ARA is a bunch of radio antennas below the surface of the ice that's intended to look for ultra-high energy neutrinos. And what we did is just replace the electronics with this phased array trigger system. And this plot on the right is really for the hardware nerds in the room, but this is trigger efficiency versus strength of signal to noise ratio. And the old trigger that people were using before, which was, I don't know, I think of it that it almost acted like a rack of NIM electronics, where it was like you open a gate, and then if the other ones, and there's just sort of a simple and between multiple antennas. That's shown in the gray line, and then just by doing the coherent sum phasing, we're improving it by about a factor of 2. This was with 4 antennas, so you get about a factor of 2. So it works, and it works just like it should in simulation. Okay, so we took that back to PUEO, and that's the way that we were able to get a significant improvement in sensitivity. Okay, so here's where we are with PUEO. We are currently in the thick of integration and testing. I wanted to put a few pictures in. Our main instrument enclosure that houses all the electronics is in the upper left, and we've been working on integrating all the systems together with the flight power system on the right. The lower right is our data acquisition system. We have half of it populated, up and running and working, and we're working on getting the rest of it together. That's in our That's in the lab test crate. And then people, some of the graduate students assembling some of the boards that go in there. We are scheduled for launch in 10 months, and that means that our hang test, which is like where you declare flight readiness to NASA, is going to be in July this summer in Palestine, Texas. So that's where we're headed to right now. So that's PUEO. I think the other thing I wanted to talk about a little bit is ground-based detectors. So that's the balloon-borne detector. So if you take a step back, ground-based detectors have other advantages, right? A balloon-borne detector is great for the highest energies because you can see a ton of ice all at once. But there's problems, right? One is you only get like a 30-day flight every 3 years if you're lucky. And so if you could get more live time, you'd love it. So ground-based experiments can get more live time. There's less man-made background to battle. Like you can probably imagine that if you build the most sensitive radio instrument possible and then fly it on a balloon, you're gonna get swamped with a lot of man-made noise. Either from satellites or people starting their snowmobiles somewhere in Antarctica, we see it all. And so so that's a bit of a, that's a struggle. So I think, going to the ground and having a more controlled environment is really nice. But the downside is you instrument a much smaller volume. So it's just a different experiment, right? Like a big volume experiment sensitive to the highest energies. A ground-based experiment is sensitive to a little bit lower energies. So that's an experiment we're building in Greenland called the Radio-Neutrino Observatory in Greenland. One of the stations is shown on the left. It's not as photogenic of an experiment as PUEO, I have to say, because most of the stuff is under the ice. But the thing on the left, the thing in the middle is a wind turbine, and then there's solar panels, because each of these things operates independently all year round. And so we need to power it with wind and solar panels. And RNO-G is currently being installed at a place called Summit Station in Greenland. We've been installing it since the summer of 2021. And the design of RNO-G really is designed to be sort of scalable to larger arrays. If someone wants to build a larger array in the future, like IceCube Gen 2, you could add a radio component and do that. Okay, so RNO-G is being built in Greenland. It's actually already the most sensitive per unit time ultra high energy neutrino detector operating. So IceCube has the best limits because they've been running a very long time, but we're turning on, and already with the 8 stations we have installed, we're more sensitive per unit time than IceCube. So as we get bigger and bigger over the next few years, that will continue to improve. So we have 8 stations installed now, and we plan to have 35 stations that are fully funded and approved by NSF, and so our next deployment season is coming up very soon this summer. That's a bird's eye view on the right, by the way. That's the skiway where they land planes. And then our array is enormous. It's a 1.25 kilometer grid, the spacing on it. Okay, this is a picture of the RNO-G collaboration, a little bit bigger than PUEO. We have quite a strong European contingent in this, actually. And it's a collaboration between quite a few institutions in Europe and in the US. So I want to talk just briefly about the Summit Station site, because I think a fair number of people in this room are probably familiar with or heard of things happening at the South Pole, but not so many things in astrophysics happen at Summit Station in Greenland. So Summit Station is right in the middle of Greenland. You get there through a town called Kangerlussuaq, and you take the same airplane that you take to the South Pole, except in the summer you take it north to Greenland. It's operated by the New York Air National Guard, just like the planes to Pole, and it's LC-130s, the exact same aircraft. It sits on top of 3 kilometers of ice, which is actually slightly more than the South Pole, but comparable. The radio attenuation length, which is what we care about for our detector, is a little bit shorter than Pole. So we actually went in 2013 and measured that. So the ice is frankly like a little bit worse than Pole. Not a lot, 10% worse than Pole. But it's a little bit worse than Pole. But we went in 2013 and 2015 to make sort of the first rounds of measurements to see if this was a good site, if the RF backgrounds were manageable, if the attenuation length was good, and if the hardware would survive. So that's sort of how we got to Summit. And these days we're building that sort of big array that you saw. So what our stations look like is we actually have some antennas near the surface, and some antennas that are relatively deep, about 100 meters below the surface. And that's because we want to get below this like snow layer called the firn into deep, clear ice so that we can see the signals well. And then we wait for a neutrino interaction and you know, look for it with our detector. So the left is just a schematic. Each station, so each dot on that array has 3 holes down to 100 meters, and it has 16 antennas total. And so we have deep antennas down the holes and an array of surface antennas that we use for a variety of things, one of which is to veto things coming from the surface. It's like an extra background rejection. So we build some electronics with that phased array triggering, we stick it in a box, we bury it under the snow, and then we lower some antennas down a hole into the ice. It turns out that drilling holes 100 meters into the ice is harder than you might think. If you had asked me like 5 years ago, how much time would you have to spend thinking about how to drill holes into the ice, I would have been like, oh, that's a solved problem. Someone must know how to do that. It turns out it's hard. So we've spent a lot of time as a project figuring out how to efficiently drill to about 100 meters, basically 1 per shift. So we can get, you know, we want to build 35 stations times 3 per station, 100 holes, right? So we need to make sure that this is efficient because it's really hard work and, you know, and it's cold and all of that. Okay, so we have a drill that we actually worked with the British Antarctic Survey to produce just for us that meets our specs, and that's a big tent that we had to build to go around it, actually to keep the drill cold, believe it or not. You'd think tent in Greenland, you're built it to keep everyone warm, but we built the tent to keep the sun off of the parts so that things don't melt while we're trying to drill. Okay, and this is just pictures of what the station deployment looked like. We built this little sled, this little hut that's movable by a snow machine, so we could just like pull it to the next one, drop the antennas down, pull it to the next one, and it has those plastic sides so that you can stay warm inside there. So that's to stay warm. The tent for the drill is to stay cold, but that's to stay warm. And then we, you know, have these shallow antennas that look like old TV antennas that I guess nobody has anymore, but LPDAs that get put in these slots, and then antennas that go down the hole as well. Okay, so RNO-G is on and taking data. I thought I would maybe just show one thing, which is that we already see cosmic rays in RNO-G. So that's like the first thing you do. Okay, the first thing you do is see if you're alive and see if you can see your own calibration signals. After that, the next thing you do is you look for cosmic rays, because we're gonna have to wait years to have the neutrino sensitivity to be better than IceCube, basically, a few more years. But immediately we can see cosmic rays in the data. So if you look in the data, you can see events like this, which is just 3 of those LPDA antennas at the surface. The simulation is in red and the event is in blue. So, you know, signals match the simulation well. We're seeing cosmic rays like we expect. Okay, and I think, you know, before I close out, I think it's worth saying one thing about, like, you know, that's what we're doing now to try to discover ultra-high energy neutrinos. Those are the experiments we're building. But people are also interested in figuring out how to expand even farther and kind of look further into the future. And so that's IceCube Gen 2. So IceCube right now is an optical detector at the South Pole. And the plan for IceCube Gen 2 is to have a bigger optical detector and in addition have a radio array, like a big RNO-G style array at the South Pole. And the reason to do this is because we add a different energy range, right? If you build an optical detector and a radio detector, you get a very broad band across lots of energy, you know, neutrino observatory. And so that's the plan for IceCube Gen 2. And you'll see on the right, the schematics for IceCube Gen 2 look shockingly similar to the RNO-G schematics. That's not by accident. That's because it's all, you know, one of the things we're trying to do is build everything in such a way that can be scalable to more stations later if we want to. Okay, so I think I'll leave it there by just saying that, you know, we're working hard building these 2 experiments, PUEO and RNO-G. They're both under construction. PUEO is going to launch in December, and RNO-G is already taking data. We're already, you know, per unit time, the most sensitive ultra-high energy neutrino detector operating. And, you know, IceCube Gen 2 hopes to push to an even bigger sort of observatory scale detector in the future. So I'm hopeful that in the next 5 years, either with PUEO or RNO-G, we'll actually discover these things. And then next time I come back to talk to you, I can tell you all about ultra-high energy neutrinos and what they look like. So thank you.
Question. There.
Yeah, thanks for this great talk. I'm curious about the localization of astrophysical sources. How do these new instruments, how would their source localization compare to like what IceCube can already do?
Yeah, so in terms of source, I think I skipped the slide because I realized I had talked too long, but in terms of source localization, so it's like, I can give you the quick answer, which is we can probably do about half a degree. Okay, that's what you can do on paper. In practice, maybe a degree. IceCube can do better than that for some subset of their events. For some of their events, their pointing resolution is terrible. It depends on the flavor of neutrino and how it interacts and what the track looks like. If it gives you a track or if it gives you, right? If it's like a muon track event, they have pretty good resolution, better than that. But if it's not a muon track event, then we'll do better. So it's not amazing pointing resolution, but you know, it'll definitely be good enough to do something. Yeah, yeah.
Thank you. I was curious if it was, my first question is it just IceCube that's also sensitive to high energy neutrinos, like other experiments like OJ too, or is it just?
Yeah, so actually, I didn't talk about it, but on this limit, there's OJ too, right? Okay, so on this plot is OJ as well. So how does OJ look for ultra-high energy neutrinos? They look for optical emission from the tau air showers. So that's what their limit is from. Their limit is from the tau neutrino interactions in the Earth that give you the tau lepton. And for them, they have these like water Cherenkov tanks. And if a shower happens really horizontally, then they have some tiny sliver where they can look for neutrinos like that. That's how the OJ limit works. Yeah.
Okay. And second, correct me if I'm wrong, but I thought it was scheduled for last year, December 24. Was there already another test flight?
For PUEO?
For PUEO.
Yeah, so we were originally scheduled for December 24, but NASA delayed us a year. Yep, because there were no launch slots in Antarctica.
In your cosmic ray event, can you take the composition from them?
I would love it if we could get the composition of cosmic rays from those events, but I think the answer is no. I think, you know, okay, maybe, right? If you had a whole ensemble of cosmic ray events where you measured the radio emission well enough, right? If the shower, so just for everyone else, so if you have a different primary particle, you'll get different shower development, right? And that shower development might be detectable in radio, but like no one has done it, right? There's probably better ways to get the composition is the short answer. Yeah.
I want to ask you a question.
Yeah.
I'll get so there. So if you're talking about those mystery events from ANITA that have the flipped phase, but then you're also saying that you can see reflections, events which are reflected on the ice. Do the events reflected on the ice flip phase?
Yeah, so I did, yeah. Okay, so I almost need like the board. Right, so in ANITA what we saw is cosmic rays, lots of cosmic rays, right? Those all have the same phase. And the reason they have the same phase is actually the cosmic ray events, so here's ANITA, it's above most of the atmosphere. Most of the cosmic ray events reflect off the ice and come up to us. They all have the same phase, but that phase is reflected.
Is the reflected
phase, right. But then the tau neutrino events will have the opposite phase because they're not reflected.
Okay.
So that's why they have opposite phase, is because like the Fresnel coefficients tell you that when the radio emission from the cosmic ray reflects off the ice, you get that inversion of phase. But for the tau event, it doesn't happen.
Okay, but the fact that you have some events with the opposite,
oh yeah,
so no matter which phase it is, you're just saying, so the mystery events are not the others, the ones that are either not reflected.
I know. The mystery events are ones that come from below the horizon with the phase that does not look reflected.
Okay, you guys have done the reflection.
Yeah. It is also true that we see in the sliver above the horizon, we also see direct cosmic ray events, right? So there's actually, anyway. Yeah.
Thanks for the talk. So this phased array where you were talking about the horns on So is the diagonal resolution question that I had earlier, is that actually just limited by the speed of the electrons? Like,
Is that limited by what?
spacing of the
Okay, so there's two things that limit the, so I could have given a more long answer to your question. There's two things that limit the angular, well, there's multiple things that limit the angular resolution. One is your baseline. That's what you're getting at, right? Is that like, that's what you're getting at, is that the farther apart your antennas are, the better pointing you have. But we're already in the regime where our ability to point the radio is not actually the dominant thing for our ability to point the neutrino back to the sky. So our ability to point the radio, you can get to like 0.1 or 0.2 degrees with PUEO, but it's the uncertainty when you, the radio emission comes from a Cherenkov cone, right? And then you have to back project the Cherenkov cone onto the direction of the shower. The direction of the neutrino and the shower are very similar because it's so high energy, but you have to know where on the cone you are, both this way and the width of the cone. That's actually the bigger uncertainty. So knowing where you are on the cone this way comes from measuring polarization. So that means you have to measure the polarization to a degree, which is hard, but not impossible. And then knowing where you are this way on the cone comes from measuring the frequency content, which is even harder. Fortunately, the cone is pretty narrow though. So you can do about a degree that way.
Okay, so essentially you're already past the limit of...
You're already past the limit where we can like point the radio well enough. You're dominated by your ability to point the neutrino from the radio. Yeah.
Okay. Any other questions? Okay. All right, well then,
Thanks.
let's thank Abby. In the forward was an NSF, and they were telling me that those C-130s going to South Pole are all the fleet.
Oh, they are.
Apart.
I know.
And
That's what I should have said. Write your congressman to get new C-130s.
Yeah, well, but our congressman, why is our